Okay, so welcome to another video on vectors, and today we're going to be applying a lot more vectors to solving physical problems essentially. So suppose we're hanging some weight of mass 10 kilograms on top of two wires, and let's say that those two wires are making an angle of 60 degrees with respect to this vertical line in the middle, and let's say that they both have the same length, just to make this a little bit clearer. So let's say some length L. Now, we want to find out what are the forces that are acting on those wires so that we know that we can choose them properly in our design. Because in any kind of engineering or science problem, we want to design something that essentially serves a purpose. And in the case of a structure, we want the structure to be strong enough to hold a specific amount of weight or load. So in this case, our benchmark is 10 kilograms. So we need to find out what are the forces acting on this whole system, and how we can apply vectors to finding the forces acting on those two wires so that we know exactly what material properties and what thickness do we need in order to be able to hold that weight without any trouble, because we obviously don't want this to break and fall on someone's head. So we want to find out what are the properties or what are the forces acting on the system so we can make a really good design. So first thing we're going to do is we're going to do something called a free body diagram. So we're going to take the middle point upon which all the forces are acting. So if I draw the forces here, we know that there's going to be some tension happening here on this rope, and on this wire and this wire. And then we have some force here. Well, actually that would go that would go here, because imagine if this is a piece of string holding the weight, then there is tension here, there's tension here, and that tension should balance out. But in general, we're just interested in the magnitude of the forces. So let's have a look at how that looks. So if we take the center point, we know that there's going to be a force here, a force there, and then the force due to the mass times gravity, so mg here. Now we're going to have some kind of straight line here, and we know that the angle is going to be the same for both of them. So let's call it theta. Let's make this more general and plug the numbers at the end so that we get a nice result. So let's call this force of tension 1 and 2, and let's draw a horizontal line here. So let's say this is our x-axis, this is our y-axis. And in general, with any statics problem, the idea is to find out the forces that would balance out this external force acting on this system. So we want a condition of equilibrium to be met. So we know that the sum of the forces, so if I write it down here, the sum of the forces along the y-axis should be equal to 0. So we want this to remain stationary at that point in space, so all the forces should add up to 0. And let's say we choose this as our positive orientation. So what we do now is we are going to add up the forces here. So we're going to start, this one is going straight down, so that should be negative mg. Now we have these two vectors here, but they have a vertical component, that's the vertical projection here. And we know that they're going to correspond to this angle. So if we grab this little projection here and put it here, then we know this is going to correspond to the cosine of that angle. So essentially we're going to have plus t1 cosine of theta plus t2 cosine of theta. So in the end, we want to solve for t1 and t2. Those are the two forces we're interested in solving. So we're going to get the following. Let's write it down this way instead. So t1 plus t2 times cosine of theta equals to mg. Therefore, t1 plus t2 is equal to mg over cosine of theta. So we have found one equation for our problem, and now the next thing that we need to do is we need to apply the sum of the forces along the x direction. So let's have the sum of the forces along the x direction. We know that they should be 0 as well. So what do we have here? Well, we have t1. Now we're going to have sine of theta. And actually this one is going negative because it is the component is pointing to the left. and then we have plus t2 sine of theta. Now this cancels out with that, and then if we move this to the other side, it turns out that t1 is going to be equal to t2, and because of symmetry, that's a result we should have expected. So in the end, if we plug this back into the first equation, we're going to get the following. Let's say that T1 equals T2 equals to the total tension along one wire, so that means that 2T equals to mg cosine theta, or simply T equals to mg 2 cosine of theta. And now if we plug in the values that we had, so 10 kilograms for the mass of the object hanging in there, 9.8 meters per second square for the gravitational constant, and then 2 times cosine of 60 degrees. So that's going to give us a tension force of 98 newtons. Because we know that cosine of 60 degrees is just 1 over 2, so that 2 cancels out with that, and then we just have 98 newtons. So that is the total tension acting on each of these wires here. So knowing that, we can actually choose the right materials and the right dimensions that would suit that wire so that it can hold this amount of weight up. So that's just another application of vectors. Essentially here what we did was break down the vectors into their respective components, y components and x components, added them together using conservation laws and using equilibrium and all that, and we actually managed to solve the problem. So this is just one of many applications of vectors, and as we will see later on, vectors have so many applications in engineering and science that without them we could pretty much not actually do a lot of these calculations, and we would be in the dark with a lot of the stuff we do nowadays. So vectors are really important, and in the next video I'm going to expand your knowledge of vectors by introducing you to the concept of the cross product of two vectors.